Concrete is one of the most flexible and widely utilized building materials on a worldwide scale. It is robust, durable, easy to maintain, fire-resistant, easy to use, and can be customized to any size or shape. Because the world's population is rising, it is critical to use a sustainable material to protect and preserve the environment. The waste demolition that are produced in construction can be used as a recycled product to maintain better surroundings. By using a sustainable product such as ceramic waste as aggregate in concrete, calcined clay and sawdust ash as cement replacement in concrete mixture, and also glass waste as replacing to a fine aggregate in concrete might give a lot of major positivity in protecting environment. So the objective of the Article 1 is to study the potential of ceramic waste as aggregate in concrete and to determine its compressive strength and water absorption. So the objective of the Article 1 is to study the potential of ceramic waste as aggregate in concrete and to determine its compressive strength and water absorption.
Next, we go to methodology of ceramic waste as aggregate in concrete. First, take the ceramic waste from the wasting area. To remove dirt from the materials, the ceramic waste was carefully cleansed. 1:4 cement ratio fine and coarse aggregate mix was used. Cubes and cylinders were tested in triplicate after 28 days. Slump tests were used to determine the workability of each of the mixtures. This method is used to ensure a uniform saturation state in the concrete, and then they were demolished and cured in water at room temperature until the test age.
This is the result for Article 1, ceramic waste that have the characteristic of the compressive strength and also for the water absorption.
The objective of Article 2 is to investigate the effect of calcined clay, sawdust ash as cement replacement in infrastructure works or building works, and also to determine its effect of compressive strength and water absorption.
Okay, next we go to methodology of calcined clay as aggregate in concrete. First, for the materials, the clay was obtained locally from the local company. It was formed into 150 mm for diameter balls and allowed to dry for 2 weeks. This was done to eliminate moisture and make the fire process easier. Following drying, the clay balls were put on crucible and calcined at 900 Celsius for 2 hours. The calcined clay is a type of clay that has been heated to a high temperature. Next, for the method, in this article, the Taguchi experimental design was used. 5% of calcined clay was added into the mixed proportion of the concrete to ensure uniformity in percentage of supplementary cementitious materials. From the percentage value, this means that both calcined clay and sawdust ash can be used as cement substitutes in concrete.
Result for Article 2, the glass waste that have characteristic for the compressive strength and also for the water absorption.
The objective of Article 3 is to study the ability of glass waste to replace concrete for sustainability, and also to investigate the effectiveness of glass as sustainable material, and also to evaluate its compressive strength as well as water absorption.
Okay, next we go to methodology of glass waste as in replacement of concrete. Based on chemical composition, waste glass is categorized into 4 types, which are soda lime glass, lead glass, borosilicate glass, and electric glass. The percentage of soda lime glass, lead glass, borosilicate glass, and electric glass usually produced were 91.5%, 2.4%, 3.8%, and 2.4%. Okay, next for the glass colors. Glass is classified into 3 colors, which are brown or amber glass, green glass, and clear or flint glass. The various colors of glass are attributable to distinct chemical composition and relate to varying color contamination limitations. While for the glass application, glass is categorized into 6 types based on application. First is container glass, and second is split glass. Next is continuous filament glass. After that, household glass or tableware and insulating mineral wool. Last but not least, specialized class.
The result for the article 3, calcine clay, sawdust ash, and also chemical admixture that have characteristic for the compressive strength and also the water absorption. Okay, I'm gonna show you the total result and discussion for the all three article, that is the ceramic waste and then the glass waste and also the calcine clay, sawdust ash and chemical admixture from the characteristic compressive strength and water absorption. For the ceramic waste, for the compressive strength, we can see that ceramic increase the compressive strength. The hardness and pozzolanic properties of ceramic aggregates are the factors of increasing compressive strength. And then for the water absorption, we can see the ceramic aggregates have a higher water absorption capacity than natural aggregates. The reason behind the high water absorption and the high water absorption capacity of ceramic aggregates is their high porosity. And then goes to the glass waste. For the compressive strength, the compressive strength of the concrete increase with the decrease of glass particle size. The glass particles tend to increase the compressive strength due to the filler effects, also known as side effects. And then go to the water absorption. The water absorption ratio decrease with the glass displacement percentage, and the gradation of glass, filler effects, and pozzolanic in glass waste can reduce the permeability. Okay, calcine clay, sawdust ash, and chemical admixture. For the compressive strength, we can see it was decreased with increase in calcine clay content. The compressive strength increased at the low sawdust ash content, and also the compressive strength increased with the crystalline base admixture. For the water absorption of the concrete mixture were observed to increase with the increase in calcine clay. The sawdust ash is very useful in reducing the water absorption of concrete. And then crystalline base admixture caused a slight reduction in concrete water absorption, while super plasticizer caused an increase in water absorption. And then goes to the result, we can see that the ceramic waste having the highest compressive strength and also the calcine clay having the highest water absorption.
In conclusion, this research has achieved the objective of determining the compressive strength and water absorption of ceramic, glass, and calcium clay. The ceramic has the highest compressive strength compared to glass and calcium clay. The irregular shape and rough surface of the ceramic aggregates compared to glass and calcium clay provide a superior specific surface area to bond firmly with cement paste. The compressive strength of glass decreases when an excessive percentage of cement is replaced with glass. There is insufficient calcium hydroxide to react with the glass. Calcium clay and sawdust ash exhibited opposing effects on compressive strength. However, it is recommended to select the appropriate type, particle size, and replacement percentage of waste glass to achieve adequate fresh and hardened properties and also long-term durability of concrete, depending on the intended application. Furthermore, the water absorption in calcium clay is higher than in glass and ceramic. Therefore, glass particles may reduce the water absorption of concrete, causes improving the sulfate attack resistance. The high porosity allows the ceramic aggregates to grip the water in its pores, improving the cement hydration. The filler effect and pozzolanic effect promote hydration and refine the microstructure, thus reducing the water absorption.
For the recommendation, the flexure and shear characteristics of ceramic particle-filled concrete members should be carefully studied. The performance of ceramic waste-based reinforced pre-stressed concrete members under static and fatigue stresses may be investigated.